So, I would like to introduce Dr. Stephen Kraft. I'm going to read a quick bio. Dr. Stephen Kraft is a founding partner at CHM Fire Consultants and has been applying his expertise in fire safety and wood construction to building designs and research over the last 10 years. Previously, he served as an adjunct professor at the Fire Safety Engineer program at the Carleton University from 2010 to 2019, and was a research scientist with Canada's National Forest Products Research Institute, FP Innovations, from 2006 to 2011. He has an undergraduate degree in forest engineering from the University of New Brunswick and a PhD in fire safety engineering from Carleton University. He is active in codes and standards development. He is the chair of the ULC S100A Fire Test Committee and is on the technical committee for the Canadian Wood Design Standard, CSA 086, where he chairs the task group on fire resistance. Dr. Kraft also chaired the NRC committee on developing the first national wildland urban interface guide, which was published early this year. He has been working with wood structure and fire safety for the past 2 decades. So with that, before we start, I just would like to go through some quick notes here. I would like to ask you all to hold your questions to the end of the presentation. And on that point, you could press the raise your hand button, and I will open your mic so you can ask directly the questions to Dr. Stephen. I would also ask for you guys that don't have a mic, or if you prefer me to read the questions for you, you just write the questions on the Q&A section. With that being said, I'll pass the word to Dr. Stephen Kraft.
Great, thank you, Vinny. Welcome, everyone. Let me just share my screen. Does that work, Vinny? Is that?
Yeah, it works perfect, yeah.
Great, okay. Well, thank you, everyone, for joining us today. I hope today's presentation will have information that's useful to each of you. I think many of the topics that I'll cover today, we could easily spend a couple hours on individually. So we will gloss over things, but I will try to leave about 10 minutes at the end of the presentation for questions. I see it's about 7 minutes after the hour now. Is there a hard stop, Vinny, at 3 o'clock?
Oh, no. If you are okay with that, we can go a couple of minutes more, just because we took some more time to start and waiting for people. We can go a little bit over.
Okay. I'll try not to go over too much. So today's presentation is really focusing on light wood frame buildings. You'll note that next week at the same time, I will be giving a presentation focused on mass timber. And so today's presentation is really limited to light frame construction for the most part. Slide. Okay, this is just a little bit of an introduction to me, but Vinny did a great job, so we'll skip over this. So in today's presentation, we'll just briefly go over the mid-rise construction requirements that were added in 2015 to the National Building Code. This was a big change, of course. Before the 2015 National Building Code, buildings were limited to 4 stories of light frame wood construction, combustible construction. And so with the changes in 2015, buildings can now be built up to 6 stories, and it created a new group of buildings that we'll look at. After we review that, we'll look at fire resistance. In particular, we'll take a look at the test method. I think it's helpful to look at the test method and remind everyone how we actually test assemblies for these buildings, and then look at some of the design options for light frame light frame wall and floor assemblies. We'll also look at exterior walls. The 2015 mid-rise provisions for combustible construction include some requirements for exterior wall assemblies, such as testing to Kenyon CS 134, which previously didn't apply to combustible buildings really. So that was new. And then lastly, I'll get into a little bit on construction site fire safety. Just touch on some of the highlights with respect to that. Again, we could spend easily the entire presentation on that alone. Okay, so as many of you are aware, and perhaps have even worked on some of the new buildings or some of the new provisions in the 2015 National Code. Combustible construction, there were two new classes created, 32250 and 32258 for Group C and Group D buildings to allow up to 6 stories of combustible construction and therefore light wood frame construction. In addition to allowing it to go up to 6 stories, this new group or building class also increases the areas of previously permitted buildings up to 25%. So you'll notice that the area for this class of building under 32250 for 5 stories, for 4 stories, let me back up. The 5-story limit of 1,800 meters square for building area with under 32251 is that for 4 stories. So the areas were bumped up by 25% as recognition of some of the mitigating features or some of the additional features, fire safety features that are incorporated into these buildings, and we'll touch on those. So now we can build up to 6 stories with light frame construction with a building area of 1,500 meters squared. Similarly for, so Group C, of course, is residential construction. Similarly for Group D, office or professional services occupancy, you'll notice the areas are significantly greater, they're double, and so we can build up to 3,000 meters squared, up to 6 stories. And so these are quite large buildings, and there's a number of features that have been incorporated into these buildings to make them safe from a fire perspective, and we'll touch on those. Just a bit more on terms of these buildings and what's permitted. So in addition to residential occupancy, Group C occupancy permitted up to the 6 stories, there are allowances to incorporate Group A Division 2, so that might be a cafe or a restaurant on the first 2 stories. Group E with mercantile, so it could be a store on the first story, for instance. And also storage garages, so basically underground parking or parking up to the, in this case, up to the 3rd story could be parking. So there's those allowances for mixed occupancy in the buildings. And of course, in some of those cases, if we have Group A Division 2 or we have Group E occupancy, then we'll have an increased fire resistance rating for the fire separation between the occupancy and Group C. Similarly, for Group D occupancy, we have Group A Division 2 and Group E on the first 2 stories, storage garage permitted up to the 3rd story. But there's also, in addition to those, which are also allowed for the residential buildings, we also allow Group F Division 2 and 3 on the first 2 stories. So these buildings, I think these provisions recognize the increased use of mixed use buildings where we have either stores or restaurants on the first story and residential above. So these provisions for mixed occupancy are used quite often. Some of the restrictions that have been placed on these buildings, the first being the height of the building, and this is This is ensuring that a 6-story building doesn't end up being a 12-story building with a mezzanine on every floor. And so the height from the first story to the uppermost floor level is limited at 18 meters. And so whether it's the 6th floor or whether it is a mezzanine above the 6th floor, that top uppermost floor is limited to 18 meters above the first floor. And that keeps the height of the building in check. Additionally, something that isn't otherwise required in the building code is the fire resistance rating for the roof. So typically in a sprinklered building, in the National Building Code, there's no requirements for roofs to be rated in a sprinklered building. However, this is an exception where in order to increase the fire safety of the building, they've added a fire resistance rating for the roof of 1 hour, similar to the rest of the building, as I've mentioned. And then there are requirements if the roof is less than or equal to 25 meters in height from the first floor, then the roof covering has to be class A, B, or C. And the roof itself can be combustible construction. However, once the roof goes over 25 meters in height, the roof has to be either non-combustible construction or fire retardant treated wood construction with a class A roof covering. So as the roof height increases, if it goes beyond that 25 meters, then provisions for non-combustible or fire retardant treated wood roof construction comes in, and that can be perhaps a bit challenging. So generally, roof heights I think are kept below 25 meters where possible. The next big change, I would say, that allows for these 5- and 6-story buildings to be constructed is an upgrade of the sprinkler system. So there's, for those that are unfamiliar, there are 2 sprinkler standards that are typically applied to these types of buildings. Up to 4 stories, NFPA 13R was permitted for residential buildings in the previous versions of the code, as well as the current version. And there are certain relaxations under NFPA 13R that aren't required under NFPA 13. So for instance, one of the big ones is an attic space for a building that's sprinklered to NFPA 13R. The attic space does not require sprinklers, whereas if it's sprinklered to NFPA 13, it does require to be sprinklered. Other things like small closets, the NFPA 13 is more restrictive on treatment for combustible concealed spaces. Things like elevator machine rooms need to be sprinklered in 13, whereas they don't in 13R. Penthouse equipment rooms and things like that. So overall, there's designing the sprinkler system to NFPA 13 will generally result in a greater sprinkler density, greater water density being applied to a fire in the event the system activates. And so we've seen in the past, particularly in Alberta, there have been cases where a 4-story light frame wood building has experienced fire, perhaps on a balcony, and it's spread to the roof and it's burned the roof off. And then of course that creates damage to all the units, particularly on the upper floors of the building. So that's a case where the building was sprinklered to NFPA 13R. So we would not expect that to occur in a building sprinkler to NFPA 13. And so as soon as these buildings reach 5 and 6 stories, the sprinkler requirements change from for residential from 13R to 13. Of course, if it's not a residential building, if it's, for example, office or Group D occupancy, then NFPA 13 applies. And balconies are required to be sprinklered if they're more than 610 millimeters deep, or that's about 2 feet deep. So any sort of usable balcony will need to be sprinklered. And that's typically done with dry head wall mount sprinklers. In addition, for these 5- and 6-story buildings, the cladding must be either non-combustible cladding or it must pass the requirements when tested to Annual CS 134. And I'll come back later in the presentation and we'll take a quick look at that test method for those not familiar. There is an allowance for 10% of the area to be of combustible cladding. So a small area can be combustible, but otherwise it needs to either be non-combustible or meet Annual CS 134 for those 5- and 6-story buildings. If it's using the greater areas of 32250, but is below, but is only 4 stories or less, then combustible cladding can still be used. Another aspect for firefighting access, in addition to the maximum height of the building of 18 meters from the first floor to the top floor, there's also a maximum of 20 meters from the access for the fire department to the top floor. So that allows for a 2 meter drop between the first floor and where the fire department access is. So you can appreciate if the fire department access is below that, that's going to limit the height of the building. And then there's also a requirement for 25% of the perimeter of the building to be within 15 meters of a street or access route. And so this is for firefighter access. And that can be, depending on the location, if it's an infill project, that can be a limiting factor on the building size. So just a couple other changes to the code for these mid-rise provisions. One of the aspects is fire blocking, and generally there's more requirements for fire blocking. So smaller areas that are permitted unless the areas are filled with non-combustible insulation. And so that's another case where the combustible concealed spaces are addressed in a more rigorous way. And then also the emergency power supply for lighting and fire alarm systems is doubled in duration to 1 hour. So you can appreciate some of these changes, particularly the sprinkler system, really add to the fire safety of the building. In general, I should point out that out of everything we do in building design for fire safety, nothing compares to sprinklering the building. So when the building is sprinklered, from a risk perspective, looking at risk to occupants, risk to property, there's no other change to the building we can make that will come close to offsetting the risk that the sprinkler system provides. And so they're very effective, and that's why they're required. So you can appreciate, here's just a picture of a 6-story project. These are highly engineered buildings. And so there's a lot of details. They're rather sophisticated designs from a design perspective, and it's not similar to your single-family home construction. These are highly engineered buildings, everything from seismic to fire performance, fire resistance of the building. So one of the aspects that needs to be considered in building 5- and 6-story buildings is shrinkage. Generally, engineered wood products are largely being used on these projects, and so we don't see we don't see large amounts of shrinkage in any one member. But when we build 6 stories, it's a cumulative effect from story to story. And so particularly structural engineer will design for shrinkage, the structure itself, and any sort of interconnection between the structure and things like elevator shafts, or if the exit stairs are non-combustible construction. Things like fire stopping. So if there's a plumbing stack and it's fire stopped through the building, there has to be some recognition that the building will settle a small amount, and particularly on the upper floors. And so design should be accounted for. Everything from building envelope and balconies, so that we don't have water. As we get small amounts of shrinkage, we don't have water pooling, perhaps on balconies or on the facade, and things like that. Seismic hold downs, which particularly in BC is a high seismic area. So the seismic designs must be able to take that shrinkage and settlement over the first year into account. And so that's something that needs to be accounted for. And which brings me next to the next issue, firewalls. Shrinkage and firewalls needs to be taken into account, because firewalls are going to be, they're not going to settle or shrink to the same degree or any, perhaps. And so we need to allow for some movement between whether it's a masonry block wall or proprietary gypsum board firewall, to allow for some movement there. And typically that would be provided by the structural engineer. There are ways, of course, to minimize that movement, whether it's precision cut studs and prefabricated walls, or whether it's the use of engineered wood products that are generally lower moisture content or have less shrinkage. So with respect to firewalls, we do see both masonry block as well as proprietary gypsum board firewalls being used. I will say that not all municipalities currently are accepting proprietary gypsum board firewalls. There's challenges in detailing those. Generally, there's when gypsum board firewalls are used, there's no penetrations put through those walls. Often there's doors that are required, and in some cases we see the vicinity of the firewall within the corridor where the doors will be being masonry block, and then outside of that it might be the gypsum firewall. So in both cases, detailing is critical, both in terms of shrinkage, in terms of acoustics, fire blocking, all sorts of all those details. And of course, any sort of ties back between the firewall back to the light frame structure will need to account for some movement. So at this point, we'll skip over to fire resistance, and I'll touch on the test method a little bit, and then just speak a little bit to design and what the options are. So likely everyone's familiar with the fire resistance test method, Cannual CS 101, in terms of the requirement in the code for fire resistance. Generally, when we require fire resistance, there's two primary objectives that we're trying to achieve. The first is to prevent the spread of fire from one compartment to another. So whether it's through temperature rise on the backside of a wall, or penetration of hot gases through that wall or floor assembly, which might allow ignition on the other side. And the other aspect is to prevent the collapse of the structure. For that reason, when we test for fire resistance, if it is a load-bearing structure, we'll test it under load. So of course, in Canada, we have Cannual CS 101. You may come across tests that have been conducted in the US under ASTM E119. This test method in the US, the ASTM test method is almost identical to that of the Canadian standard. There are a couple small differences, but in general, when tested to the ASTM method, it's in general, it's likely applicable in Canada. And then other parts of the world, including Europe, Asia, Australia, New Zealand, use the ISO method, ISO 834. It is slightly different, has a slightly different temperature exposure. And so it's not very common that someone's looking to use an ISO 834 test in Canada, but from time time to time it does happen. So just a little bit on the test method, and we'll look at the furnaces that we test these on. In general, we're trying to test construction that's representative of what's being built in the field in terms of materials and workmanship. When we're testing a load-bearing wall, for instance, we'll load it in the test frame, and we'll see that in a second. Of course, walls may or may not be load-bearing. Floors are always going to be load-bearing, and of course, beams, columns, and other structural members will always be load-bearing. To give you an idea of the size of assembly that we're testing, in the standard test, usually most furnaces are on the order of about 10 feet by 10 feet. So for a wall assembly, that's the size that we're testing. Of course, we're testing it in order to extrapolate those results to walls that are taller and wider. So, and similarly for floors, typical floor furnace is on the order of 4 by 5 meters, or perhaps 14 feet by 19 feet, something on that order. Just quickly, in terms of the fire exposure that we're applying, or that we're exposing a wall or a floor assembly to, or perhaps a column, the intent originally is to represent what we call a post flashover fire, so a fully developed fire in a compartment that's limited in size only by the oxygen that's able to get in that compartment. And so you'll see that in the first 20 minutes or so, we're already up to probably about 750 degrees Celsius. So that's already getting very hot. And of course, at an hour, we're at about 927 degrees Celsius and over 1,000 degrees Celsius at 2 hours. This does continue out to 4 hours, this curve, but most assemblies we test are 1 or 2 hours, perhaps, or less, 45 minutes. Here's a schematic of a floor furnace. This is taken from the Canadian standard Kennual CS 101. But this is pretty typical for a floor furnace to test floor assemblies. So we have a large plenum in the bottom portion of the furnace, where there's a number of gas burners that are reproducing the fire temperatures inside this plenum. Usually there's observation ports that allow us to see inside. And we have the floor assembly, which sits on top and makes up the top of the furnace. And you'll see there's thermocouples measuring the temperature just below the floor assembly, and that's measuring the temperature. And so the furnace is controlled to follow that temperature time curve on the previous slide. What's not shown here is loading being applied to the top, which we'll see in the next photo. This is the floor furnace at the National Research Council in Ottawa. And just like that previous picture, we can see the bottom portion of the furnace with the plenum and gas burners. Gas burners in this case are on the sides, reproducing that fire exposure inside. These ports where we see the soot deposits above are the viewing ports to be able to see inside and see how the floor is responding to the fire exposure. And then the floor sits within this large steel frame that sits on top of the furnace. And in this case, the floor is being loaded using these hydraulic jacks, which we'll see closer in a moment. So generally, when we test a floor assembly, we have a uniformly distributed load applied over the full floor assembly. Similarly, for a wall furnace, same kind of premise where we have a plenum where the gas burners are reproducing the temperature time curve within this plenum. We have thermocouples measuring the temperature in that space, reproducing that fire. We have viewing ports on the sides, and then we have a test frame where the wall assembly sits within this test frame. Usually there's hydraulic jacks either above or below that allow the wall to be loaded. Here's a picture of the floor furnace at Intertech down in San Antonio, Texas. In this case, we're testing a CLT wall assembly You can see there's hydraulic jacks below, hooked up to a hydraulic pump that maintain the load. And there's a viewing port on this side you can see into the furnace. And so that allows us to test for the fire resistance of the wall assembly. You can also see in this case, there's thermocouple pads on the unexposed side of the wall where the temperature is being measured under those pads for one of the failure criteria, which we'll touch on in a minute. So just a quick note on load. Generally speaking, when we test for fire resistance, generally we load wall and floor assemblies to the full, basically the full design load. It's in the standard, it's called the full specified load condition. And so that's generally how we test assemblies. However, in some cases, for one reason or another, we may decide to test at a lower load, and then that would be reported, whether it's in a test report or in a subsequent listing. There would be a restricted load use condition. So there'd be a restriction on the load that could be applied for that particular fire resistance rating. So that's one thing to watch out for. Here's an example, again, at the NRC furnace of the hydraulic system above, applying a uniformly distributed load to the floor assembly. So I think it's important to understand the failure criteria for fire resistance. Now there's 3 failure criteria, and all 3 may not apply to every assembly. So for instance, well, let's go through them first, perhaps. So if we're testing a wall assembly, for instance, that's load bearing, all 3 of these would apply. So first is transmission of heat. So during the test, the average temperature measured on the unexposed side of the wall shall not rise more than 140 degrees Celsius above the initial temperature at the start of the test, or at 180 degrees Celsius at any point. So that's looking to prevent fire spread from one side of the wall to the other. Support of the load, so the test specimen shall sustain the applied load throughout the test. And then lastly, passage of flame or hot gases. The assembly shall prevent the passage of a flame or gases hot enough to ignite a cotton pad on the backside. And so this is really looking at the ability, again, to contain the fire. So you can appreciate for a load-bearing wall, all of these would apply. For a non-load-bearing wall, only the transmission of heat and passage of flame would apply. And for a beam or a column, only the supportive load would apply where it's not a fire separation. Okay, so just real quick, generally speaking, these mid-rise wood buildings, anything 4 stories to 6 stories is going to require a 1-hour fire resistance rating for the floors and, of course, the supporting structure. So in the case of light frame construction, that would be the walls, are going to require a 1-hour rating. If we have mixed occupancy, there's such as mercantile on the first floor, or perhaps a restaurant, A2, then we'll have a 2-hour fire separation between that occupancy and the occupancy above, if it's residential. So, but for the most part, these are 1-hour fire resistance rated buildings. And if we look at, from a design perspective, what are our options to design the building for fire resistance? First, there's a component additive method in Appendix D of the National Building Code. And I will mention that it's been significantly improved from the 2010 version. So there's a lot more combinations of assemblies now that can be designed using that. And we'll take a quick look at that. And then, of course, there's listings from whether it's ULC, Intertech, or QAI. And in addition to those listings, or perhaps I should say, those listings can be found in the published directories from each of those organizations. Although sometimes honestly, those directories can be a bit cumbersome to find assemblies in. So other methods, often manufacturers in their literature will cite their listings that they have and provide perhaps links or at least listing numbers. Another great resource is the Gypsum Association's design manual. So they have many light frame, wood and steel frame assemblies in that manual. And where applicable, they will reference the listing if there is a listing, or perhaps other test data that was used for that assembly. So if we just look quickly at the component additive method, so the original component additive method was based on tests that were completed in the 50s, 60s, and 70s, and it wasn't significantly updated until just in the last edition, the 2015 National Building Code. And there were probably something on the order between perhaps 80, 90 fire resistance tests that were conducted at NRC in the 2000s, or perhaps late 90s, 2000s. And so that information was used to update the component additive method. And we'll see on the next slide that there's a lot more combinations of materials. So it's important to remember, though, the component additive method can only be used to determine fire resistance ratings up to 90 minutes. So when we have 2-hour assemblies in light frame, we need to go to either listings or another method. The assigned times, yeah, so one of the challenges with the component additive method that we see is that it's often used inappropriately when numbers are cited from or different components on their own. So for instance, if we look at the next slide, where we have a table for gypsum board membranes. For instance, if we have 5/8 type X gypsum board, giving 40 minutes, that's 40 minutes when it's applied to a frame, whether it's wood frame or steel frame, with all the other components of the wall assembly. And so we can't extrapolate this out and say that gypsum board, 5/8 type X gypsum board on its own gives 40 minutes. It's part of a calculation. And so that's the important thing to remember with the component additive method. The other aspect, which is less of an issue now that we see, is that we have a lot more combinations of gypsum board, for instance, now. In this case, this is for floors. So we've got 1 and 2 layers of both 1/2" and 5/8 type X gypsum board at different stud spacings, giving different results. And so some of the challenges before, for instance, someone might look at the table and say, if one layer of 5/8 type X gypsum board gives me 40 minutes, then 3 layers would give me 120 minutes. Well, no, we can't do that. We can only use what's in this table. So single and double layers now are provided. Previously, there was only 2 layers of 1/2". And so I think that was more of a common misapplication than it will be now. But the other thing to keep in mind is under the component additive method, each of these times or most of them have little notes below the table, and whether it's restrictions on its use. So it might, for example, note 3 applies to wood joists, wood trusses, wood eye joists, and cold form steel studs. So there's something being left out there. I'm not sure offhand which one it is, but each of these have those footnotes. But also, in addition to this, later on in this section of Appendix D, there are requirements for the framing and for fastener spacing and for exterior walls, the sheathing, which need to be adhered to as well in order to use this method. So it's important to read all of the notes and requirements and not just look at the tables. For listings, listings are one of a very common way particularly for manufacturers to test and market their products. So I mentioned there's generally 3 accredited certification organizations in Canada providing listings accredited by Standards Council Canada. Includes ULC, Intertek, and QAI. There are others accredited, but those are the main ones that are providing listings for building products in fire. So one of the important things to recognize, I think, with a listing is that it's not just the fact that the material has been tested and successfully completed the test, but part of that listing is the quality assurance that goes behind it. So the accreditation or the certification body will make sure that the product is being manufactured under a quality system, so that the product that's used in a year from now will perform the same as what was tested. And they'll often do periodic testing of the products to make sure that the product's not changing over time. So there's follow-up, basically, as opposed to a manufacturer using a fire test from perhaps 20 or 30 years ago. And so there's no check to say that what is being manufactured today is the same as what was tested 20 years ago. And the other aspect of that is that when a product is being tested for certification under a listing, that product is also sampled as well. So there's some assurance that the product being tested is actually representative of what they're producing. So listings have many benefits in that respect. And of course, they're applicable to Part 3 or Part 9 buildings. And then I just have a quick example here of a listing. It's really just the picture. But what I want to point out here is that often there'll be notes with the listing. So in terms of the fire resistance rating, generally, if there's any load restriction factor, it will be stated here. So for instance, this particular listing has the statement, this design was evaluated using a load design method other than limit states design method. Example, working stress design method. For jurisdictions employing the limit states design method, such as Canada, a load restriction factor shall be used. And it points you to a guide where it provides a reduction for, in this case, for walls. And this particular listing, I'll also mention, is 12 pages long. So not only are there many components, there's the components we see numbered here, but for each of these components, or for many of them, there's a number of different manufacturers that have been able to have their product added to this listing. So for instance, there's 10 or 12 different gypsum board manufacturers that are listed for being acceptable in this assembly. There's different installation options and whatnot. So in addition to specifying fastener spacing distance and whatnot. So of course, it's always important to look through the listing and make sure all the details are being followed. Lastly, I'll just mention the generic tables under Part 9 of the Building Code. These tables, again, similar to the component additive method, were significantly increased in number in both 2010 and 2015 national codes based on the testing that was done at NRC. I think there's hundreds of assemblies now that are in these tables for providing both fire resistance rating as well as sound transmission class ratings. However, it's important to point out that these are in Part 9, and so these are not applicable to Part 3 buildings. If you're designing a Part 3 building, then you cannot rely upon these generic tables. So you'll have to either use the component additive method or listings for fire resistance ratings. So moving on to exterior wall assembly, as I mentioned, for mid-rise 5- and 6-story light frame buildings, the code requires either non-combustible cladding or cladding tested to CAN-UL CS 134. So one thing I should point out is that CAN-UL CS 134 as a standard is testing an exterior wall assembly. It's not just the cladding that we're testing. And so this is one of the challenges in applying CAN-UL CS 134 test results, is that it's very difficult to test every possible combination of materials that are used in exterior walls, because from one project to the next, there's often differences. The other aspect I'll point out is that this test method is, as we'll see on the next slide, is it's a full-scale test method. It's a full 3 stories high or 34 feet high, the test apparatus. The test sample is on the order of about 33 feet high, so it's a full 3 stories. It's a very expensive test method, so it's not one that that a manufacturer will test over and over with different combinations of insulation, for instance, because of the cost. In general, it costs the manufacturer something on the order of probably close to $100,000 to run this test, which is very unfortunate because it means we have very few tests, few listings to this test method. But with that being said, it's a very robust test method, so we have a lot of confidence in the results. So just a little bit on the test method. It's 3 stories high. The minimum dimensions roughly 16.5 feet wide, and there's a compartment in the first story with a window opening. And this window opening basically allows a fire to exit the compartment and expose the exterior wall to a fire plume. Just before I go to a picture of the fire exposure, I'll just point out in terms of duration, it's a 25-minute fire exposure, and the fire exposure ramps up from basically from at 0 minutes, the fire just starting, to at 5 minutes, the full amount of gas flow is flowing. So it's at its most severe from 5 minutes through to 20 minutes. So it's 15 minutes at the full exposure, and then linearly it ramps down from 20 to 25 minutes. So 25 minutes overall exposure with 15 at the peak. It's very hard to appreciate from these pictures the fire severity in this test, but having witnessed a number of these tests, it's a very severe fire exposure. And basically we have propane burners in the room that are producing, basically putting out more propane than can be burnt in the room, and that's why we have the fire plume exiting the window and extending up the facade. There's 2 failure criteria in this test method. One is we're looking for flame spread on the exterior wall or in the exterior wall. And if that flame spread reaches 5 meters above the window opening, then that's failure. Also, there's a series of 3 heat flux gauges, 3.5 meters above the window. And those are measuring the heat flux back to the wall. So basically the radiation back to the wall. And if the exterior wall is contributing to this fire plume that's going up the exterior, and if it contributes too much, then we will see failure based on heat flux. So if the heat flux goes over 35 kilowatts per meter squared, measured at that 3.5 meter height, then that also constitutes failure. To give you an idea, fire retardant treated plywood can pass this test. It's kind of borderline. Sometimes it might pass, sometimes it might not. And so that's the level of performance that's required to pass this test. And it's a very severe test and can be challenging to pass. So this is just quoting the 2 failure criteria I just mentioned from the code. For design, there's, like I said, that there are some listings available. There's not a lot of listings available, honestly. And those listings are generally for high-rise buildings where this test method's been applied to previously. And so for mid-rise buildings, there's not, on combustible construction, there haven't been many tests. In fact, I think that the only tests are likely the ones that have been done for research. And so to that end, the next version of the National Building Code, which is currently being finalized or going through publication right now, which should be published by the end of this year, I believe. So that will be either the whether they call it the 2020 National Building Code or 2021, that will have 5 generic exterior wall assemblies, which could be used on combustible construction. So they did tests with both fire retardant treated plywood as well as gypsum board over insulation, as well as they did a test with mineral wool insulation over cross-laminated timber. And in each case, the tests were successful. And so those are being added in a generic basis to the Appendix D of the National Building Code coming out later this year. So there will be more options in the near future. So today for design, there are limited listings available. Some manufacturers have test reports they use as opposed to having listings. Of course, there are, as I mentioned, there are perhaps some drawbacks to that, but in any case, the building code does say you need to demonstrate performance via the test method. So that's often used. And then lastly, engineering judgments. We do have the research test from NRC, which allows us to do engineering judgments from time to time, depending on the circumstances. So that wraps up exterior walls. I think the last few minutes, I'd like to touch on construction site fire safety. For combustible construction, this is commonly a concern, particularly by the fire service. And I would say this is one of their biggest concerns when we adopted mid-rise construction in Canada of combustible construction. So just a few things to kind of put construction site fires in perspective. Construction site fires are rare, but when they do happen, they can lead to very large fires and large losses. So construction site fires represent less than 2% of all fires. Generally, civilian loss of life and injury are low because often these sites are not occupied when fires happen, which we'll see in a minute. And property damage is often higher than average for construction site fires because we don't have fire safety features in the buildings yet. And in some cases, generally when these buildings are in close proximity to other buildings, we can have much, much larger losses in the tens of millions. So why are construction site fires a greater risk, or a fire during construction can be a greater risk? There are many of the features in a finished building that are not yet in place. So fire alarm system and sprinkler systems generally are not operational during construction. We often don't have compartmentation of the building because the gypsum board fire separations have not been constructed yet, and perhaps firewalls may not be up yet. Limited or no structural fire protection. So particularly in the case of light frame, you can appreciate light frame construction has very little fire resistance on its own without the gypsum board. Gypsum board provides 95% of fire resistance for light frame construction. And so without gypsum board, the structure does not take long to start collapsing. Of course, we have, in addition to light frame, we also have the exterior sheathing and possibly some combustible insulation exposed. These sites are also at greater risk for arson and incendiary fires because the site's unoccupied during non-working hours. And we also have hazardous activities such as hot work taking place on site during this vulnerable stage. So that all sounds pretty grim, of course. I think we need to look at this in perspective, and that the construction phase is a relatively short period of time in the lifespan of the building, and we can take steps to mitigate these risks during construction. In order to mitigate those risks, so it's helpful to look at what are the main causes of construction site fires. This is a study that US Fire Administration completed 20 years ago now. But you'll notice that the two main causes of construction site fires are incendiary suspicious, so that would be arson, on the order of 40% or over 40% they found. And open flame, so that's largely representing hot work, on the order of 30%. So right there, 70% of fires between suspicious and open flame. And then lesser things like smoking, heating on site, electrical distribution and whatnot. But you can appreciate if we can tackle those first two, then we can go a long way to addressing construction site fires. Another study by NFPA, again, 20 years ago, found similar numbers. 40% were incendiary or suspicious, open flame, ember, and torches at 21%, heating equipment at 10%. So similar findings. And then lastly, in BC, more recently, there was a study looking at fire statistics from 2005 to 2009. So over that 5-year period, there are 275 fires, construction site fires, and 63% were reported as incendiary, and 22% were undetermined. Over those 275 fires, there were 10 injuries, 1 fatality, and property loss of 53 million. One of the interesting things was they looked at timing of these fires, and no surprise, the incendiary fires typically occur during off hours. And also more than half of the construction site fires started on a ground floor. So just a note on that, site security can be quite important to mitigate those fires caused by arson. And so, you know, whether it's having site security or making sure that first story is boarded up with, you know, perhaps a set of steel doors and for entrance and windows closed up, can go a long way to keeping the site secure. I won't go through this based on time, but just point out that many of these large loss fires over the last 20 years in Canada, there's some really big ones, 66 million, 38 to 60 million. There's, in each of those cases, you'll notice that it was because there are neighboring buildings. But if you go down through and look at the causes, propane heaters, roofer's torch, propane heater, roofer's torch, propane torch, arson. So again, it follows these statistics, but a lot of the large loss fires are caused by roofer's torches because that's at a point when the building is quite vulnerable, because generally when the roof is just going on, the gypsum board hasn't been installed yet. So that's a note of caution. So I won't go through the regulations too much, but just point out that the National Fire Code does have some requirements for construction site fire safety, both for hot work as well as site safety. There are some guidance documents that have been written for BC and Ontario who've adopted the mid-rise a bit earlier, because you can appreciate the concern with 5- and 6-story light frame buildings is much greater than it was previously when we were building 3- and 4-story buildings. But in addition to those those requirements in the National Fire Code, often there's local or provincial occupational health and safety regulations as well. And then there may be local bylaws, and insurance providers often have their own set of requirements that they're looking for the builder to follow. Things like hot work permits and whatnot. I will point out there were some changes to the National Fire Code for the 2015 National Fire Code to reflect the changes to the building code to allow mid-rise wood construction. I'll just touch on a few of these. So designated smoking areas, signs at the entrance of the property with the street address, and signs in the stairwells on each floor with the street address, floor level, stair location, street address. And that really comes down to a worker calling in a fire on site and having that information right in front of him, as opposed to trying to describe where the project is. Oops, sorry. Things like dumpsters and bins where they are placed next to the project. Water supply has to be available when the combustible materials show up on site. Strong construction fencing is required. And minimum requirements for exits during construction. So a fire safety plan is required in the National Fire Code. And so there are some documents available for guidance, particularly out of BC, that are quite helpful in developing a fire safety plan. But some of the key steps are analysis of the site. So what are the risks? You know, is it next to an apartment building that with people sleeping at night, and therefore that's obviously going to be a greater risk than perhaps a building being constructed with no buildings around it. Development of policies and procedures to minimize risks. So hot work procedures and perhaps designing out the need for hot work, whether it's welding or whether it's plumbing, using materials that don't require hot work is a great way to avoid it. So whether it's bolted connections or press fittings for plumbing, that sort of thing. Analysis of available resources, and then an emergency protocol for various individuals. So who's responsible for what? That's a key part of developing the fire safety plan. There's a list here, I won't go through them, of some of the key aspects of a fire safety plan. Excuse me. And lastly, I'd just like to wrap up with a mention of some testing that's going to be taking place in Ottawa next year. And I will talk about this a bit more next week during the webinar on mass timber, because this is really related to mass timber. We're building a two-story structure that is quite significant in size. It's on the order of about 23 meters long and 15 meters deep, two-story structure, and we'll be doing a series of 5 different fires in this structure. The picture on the left is a demonstration test that we were working on earlier this year in Richmond, BC, which was smaller scale. Perhaps we call that a medium scale, where it was about 20 feet by 20 feet in this photo. But really looking at fire performance of mass timber. So that's just a bit of a tease for whether you're coming next week to the webinar, or whether or just to keep an eye out for that, as we'll be live streaming. I expect these tests next spring, early summer. So with that, I would be happy to take questions, and I hope that this has been informative and useful to the participants.
Yeah, thank you very much, Stephen. If anybody has questions, please hit the raise hand button so I can unmute your mic and you can ask the question directly.
Uh-oh, I've put everyone to sleep.
No, I don't think so. Well, if we don't have questions, we will wrap it up. And thank you very much for your participants, and thank you again, Stephen. We will see you next week again.
Great. Yes, I look forward to it. The presentation next week will be looking at some of the tall mass timber projects in Canada that we've been working on, as well as talk about alternative solutions for tall mass timber buildings, and get into the mass timber side of things, which is perhaps a little more interesting from an architectural standpoint.
Yes, absolutely. Thank you very much.
Okay, thanks everyone.